It's date 7 on 13th summer school at LHC Physics. Today is very special day because many other foreigners visit today at NCP. First of all, we have a 13th summer school on LHC Physics ceremony at 9 p.m. Then we have a talk on CMS experiment by CMS spokesperson. Very interesting. The next is Franz Hartmann. He is coming from Germany and he will talk about radiation hard silicon detector. Interesting. And the next is Christian Allen Heck. He is coming from United States of America, USA. He will talk about different things like triggering the tracker in CMS. Quite interesting. The next is Thomas Muller. He will talk about the top quark. Okay, so today all the foreigners is also coming from Germany. We will have a great meetup with these foreigners, and we have hands-on experience on lab. And today we will visit labs physically, and we have a great meetup with these foreigners. So today's point is that having a problem is half of the solution. So if you have a problem, no problem is basically 50% of the solution. So thanks for watching. Stay tuned with me. I'll update you each and every day.
They say to run when it all goes dark, but I know where I'm gonna be. Next to the girl with a broken heart and a temper like the fallen leaves. I want to help you, I'm nothing without you. With music, it needs you, and I do. I breathe you. Try to erase us, the look on their faces when they thought they'd break. We were ready for the earthquake. For the earthquake. They say to run when the ground starts shaking, but I know where I'm gonna be. Next to the girl who can take my heart and fulfill my every fantasy. I want to help you, I'm nothing without you. With music, it needs you, and I do. I breathe you. Try to erase us, the look on their faces when they thought they'd break. We were ready for the earthquake.
About the statistics and physical sciences, especially it will be, I think, focused on the high energy physics. And then we have two lectures on W and Z boson, so electroweak physics at the LHC and future, and even in future colliders. So you already have attended these two lectures from Robert and team. And series of lectures, 4 lectures, I think 5 lectures from Thomas Muller and top quark, from discovery to precision. So from the old days, he was a part of these experiments, so we will be explaining whole things also, like how the top quark was discovered and everything, and then how it converted into precision physics. And Frank will be giving series of lectures on the radiation hard silicon detector and also on the CMS upgrade. So the first lecture will be today. Christian, he will be giving a series of lectures on triggering the tracker, silicon tracker at CMS, and also about the performance of the CMS tracker. Then there will be also a lecture from Albert Dior regarding the DSM circuit. Rebecca, she will be talking about the neon system. And then there were dedicated lectures that I think we have attended about the the physics object at CMS.
Origin of mass, to understand why there are so many elementary particles with different masses, why different forces between particles differ from each other, and search for an ultimate theory of matter. In LHC, superconducting magnets have been used for bending the particles' beams, and it is operated 300 degrees below room temperature. It is now the most powerful accelerator on Earth. The 2 weeks LHC school is focused on the physics and detector technologies of the LHC experiments at CERN. Collaboration with CERN in the area of experimental high energy physics and related disciplines was started by PAC and NCP. The collaboration began with the signing of a cooperation agreement in 1994 by PAC, which for the first time opened the doors for Pakistani scientists to visit CERN and explore areas of mutual cooperation. The National Center for Physics played a pivotal role in developing scientific collaboration with CERN and in the development of high-energy physics programs in the country. The experimental high-energy physics program was started from scratch at NCP, and over the time, more than 100 MPhil and PhD theses were completed on the CMS experiment at CERN. Most of the students trained by NCP are now working in different universities and R&D organizations around the country, and many succeeded in securing research positions abroad. To further raise the collaboration level between Pakistan and CERN in 2013, BAC started negotiations with CERN to pave the way for Pakistan to become associate member. The formal application was submitted to CERN Council in February 2013. It took about 2 years in resolving all the technical administrative issues, and finally Pakistan became associate member of CERN on July 31st, 2015. This important milestone was achieved due to the hard work of NCP and PAC scientists and engineers. For CERN being a multilateral leading scientific organization, the associate membership of Pakistan opened a new era of cooperation that will further strengthen the long-time partnership between CERN and the Pakistani scientific community. NCP and PAC first started contributing to the RPC project at SCMS. Our RPCs are still used in data taking since 2009. Both NCP and PAC contributed to the assembly of gem detectors, which are now being used in the Run 3 data taking and XCMS. NCP has excelled in terms of physics, analysis and detector technologies, and has advanced towards technological sophistication by taking part in the upgrade of the CMS Silicon Tracker. As a result of the project, state-of-the-art silicon detector lab has now been developed at NCP. NCP is now one of the 6 silicon sensor qualification centers of CMS. One of the 8 silicon module assemblies and testing center, and the only center of CMS where aluminum carbon fiber TB2S ladders are being produced. As member science at PAC, I supported and assisted in the approval process of the project by the Planning Commission. Training of young researchers and giving them the opportunity to work on the analysis of LHC data is very important scientific pursuit. It is promising to see that the activity has benefited large number of students from all over the country and abroad. The school provides excellent opportunity to interact with leading faculty in high energy physics and to learn from them. All the participants should benefit from the 2 weeks school, especially to learn how to search for new physics by analyzing wealth of LHC data and to prepare themselves for the challenges in the LHC Run 3.
Professor Jonas Redmaker from University of Bristol, United Kingdom. Professor Christian Alan Hahn from Northwestern University, USA. Dr. Markus Wallerberger from Austria. Our guest of honor, please. Thank you, everyone. This concludes the welcome session of the school. Now we depart for the group session. That will be followed by the tea. So the participants would go to the cafeteria, and the rest of them would be served the tea just outside the auditorium. Thank you very much, and we'll leave for the group photo, please. Thank you.
They say to run when it all goes dark, but I know where I'm gonna be. Next to the girl with a broken heart and a temper like the fallen leaves. I want to have you, I'm nothing without you. When music, it needs you, and I do. I breathe you. Tragic erases the look on their faces when they thought they'd break us. We were ready for the earthquake. For the earthquake.
लेकिन ये अगर वो आप देखेंगे ना कॉर्नर में स्क्रीन के ऊपर तस्वीर देखेंगे तो जो 3 प्रोब नजर आ रही है उस कॉर्नर में जो कि हर एक जो डायोड है वर्किंग एज इंडिपेंडेंट सेंसर तो पिच या डिस्टेंस बनाए गए हैं और ये जो सारा स्टेप पॉलिसिलिकॉन रजिस्टर है उसके थ्रू हम इसको बायस करते हैं और बैक लाइन जो होती है वो उधर रखते हैं अपने प्रो स्टेशन के चक के ऊपर। तो ये जो सेंसर है ये हाई टेक टेक्नोलॉजी बेस्ड इंडस्ट्रियल प्रोसेस है जो कि ऑफ कोर्स ये किसी डायर में इस तरह से नहीं हो सकता। ये जापान में बनते हैं। जापान जो कंपनी है वो इसको बिल्ड करती है और फिर ये डिस्ट्रीब्यूट करती है टू सर्न को भिजवाती है। जितना भी सर्न में ट्रैकर सिस्टम के लिए सेंसर है बेशक CMS क्यों एक और एक्सपेरिमेंट एटलस उसके जितने भी हो वो सारे यही कंपनी बताती है क्योंकि उनके साथ तो ये प्रूव्ड है कि ये जो टेक्नोलॉजी इस तरीके से ये एफिशिएंटली बना सकती है। तो वो जो सर्वर भेजे उसके बाद 6 सेंटर है उनमें से हम एक इंडिया में है, एक ऑस्ट्रिया में है, एक जर्मनी में है और 2 USA में। तो सेंटर भी सेंसर डिस्ट्रीब्यूट करते हैं। तो वो हम जो इनका एक मानव सेंटर हमारे पास भी ये सेंसर आते हैं और ये सेंसर ऐसे नहीं भिजवाते, उनके लिए एक सर्टन सेट ऑफ क्राइटेरिया है जो कि हमें फुलफिल करना पड़ता है। तो फिर वो कहते हैं कि यू आर कैपेबल टू क्वालिफाई दिस सेंसर। तो वो कैपेबिलिटी क्या है? वो ये जो कॉर्नर में आपको ये सेटअप नजर आ रहा है जिसकी जब वो लाइटें वगैरह ऑन है। तो ये एक इसको कहते हैं SQC हायर हाँ इसको प्लीज इसको कहते हैं SQC, सेंसर क्वालिटी कंट्रोल या करेक्टराइजेशन फैसिलिटी।
Yes, sir.
इसमें यह है कि ये प्रो स्टेशन जो भी ये मर्करी खोलते हैं, ये एक प्रो स्टेशन है। प्रो स्टेशन में जो बेसिक जैसे चीज़ें होती हैं वो होती है ये जो नीचे आपको एक बेस प्लेट से नजर आ रही है, ये चक है। तो ये चक जो है ये XYZ में विद इन 1 माइक्रोमीटर पर सेकेंड के साथ मूव कर सकता है और इसको हम कंट्रोल भी कर सकते हैं थ्रू लैब सॉफ्ट जो कि हमने अर्ली कर भी है। उसके बाद इसके ऊपर हाई रेजोल्यूशन माइक्रोस्कोप लगी हुई है जिससे वो आपको वो जो इमेज है वो डिस्प्ले हो रहा है। हेलो लगा तो वो हमें हेल्प करती है उसको करने के, बाकी हम इंस्पेक्शन करनी है वो भी इसके लिए बस कर सकते हैं। तीसरी चीज़ है ये है कि ये अगर हम डोर क्लोज कर दें, अंदर इसके अंदर सिस्टम लगा हुआ है जो इस ह्यूमिडिटी को विद इन लाइक 5 यूनिट्स, अगर बाहर 60% ह्यूमिडिटी है या 70 है तो विद इन 5 और 10 मिनट्स ये 10% ऊपर लेके आता है। इवन तो अगर हम नीचे भी करना चाहें तो उसको हम रिड्यूस कर सकते हैं लिमिटेड टाइम। उसके बाद उसका जो टेम्परेचर है चक का वो हम कंट्रोल कर सकते हैं। वो वैसे हम इसको 20 सेल्सियस रखते हैं, ऐसे नीचे भी हम कर सकते हैं, ऊपर जैसे हम चाहें वो उसको कर सकते हैं। उसके बाद ये जो आपको प्रोब नजर आ रही है ऊपर ब्लैक कलर की और नीचे भी वो पड़ी हुई है, तो ये विद इन 1 माइक्रोमीटर की प्रेसिजन के साथ आप इसको मूव कर सकते हैं, प्लेस कर सकते हैं जहाँ पे आप इसको रिक्वायर्ड है। तो ये जो सारी चीज़ें हैं ये बड़ी हेल्पफुल होती हैं जब हमने एक सेंसर को ऊपर इस चक की बना के इसको क्वालिफाई करना। और उसके सबसे इम्पोर्टेंट चीज़ है कि जब ये सेंसर प्लेस करते हैं तो नीचे वैक्यूम से ये सेंसर बड़ी सख्ती से होल्ड कर लेता है चक। तो उससे हम ये मेक श्योर करते हैं कि सेंसर आपके प्लेस पे रहेगा, कहीं भी मूव करेगा। उसके बाद आपको जितनी भी प्रोब और सारा कुछ होता है वो हम इसको इंस्टॉल कर देते हैं केबल बंद करके। इसके बाद फिर हम इसकी जो मेजरमेंट हमने लेनी होती है वो लेते हैं। उसके बाद ये जो लेफ्ट साइड पे एक रैक नजर आ रहा है जिसके अंदर आपको लाइटें और स्ट्रक्चर नजर आ रही हैं। तो ये सबसे जो बॉटम में पड़ा हुआ है इसको LCR मीटर, तो ये यूज होता है हम जो कैपेसिटेंस मेजर करते हैं। तो एक सेंसर के लिए हम 8 पैरामीटर मेजर करते हैं, उनमें से 3 जो है कैपेसिटेंस की मेजर करते हैं, उसमें एक ग्लोबल कैपेसिटेंस है और बाकी 2 और एक कंपनी कैपेसिटेंस, इंडस्ट्रियल कैपेसिटेंस। इसके ऊपर एक जो मीटर है उसको हम बायसिंग के लिए इस्तेमाल करते हैं। जब भी हम सेंसर टेस्ट करना तो उसको बायस करना जरूरी है। बायस मीन टू क्रिएट द डिप्लीशन रीजन और उसको एक सेंसर के तौर पर बात करा, अदरवाइज वो एक जस्ट मटेरियल है, वो सेंसर नहीं है। उसके अंदर जितना हमारे लिए लेक्चर में डिस्कस कर चुके हैं उसके अंदर जो कैरियर होते हैं बहुत ज़्यादा होते हैं और हमारा सिग्नल उसके अंदर कुछ भी नहीं, तो इसलिए वो उसको बायस जरूरी होता है। और जो एक डिप्लीशन रीजन बनता है वो वर्क एज ए सेंसर करता है।
First, product student experiment research start कर ली थी and then ये आपको नजर क्या आ रहा है कि पैकेलाइट इश्यू तो हमने रिसर्च के बाद किसी रजिस्टर प्लेट चैनल
Don't start shaking, but I know where I'm gonna be. Next to the girl who can take my heart and fulfill my every fantasy. I want to have you, I'm nothing without you. My music, it needs you, and I do. I breathe you. Try to erase us, the look on their faces when they thought they'd break. We were ready for the earthquake.
Data, and then we sum over all possible results. So one possible result is 1, and then we weight this possible result by the probability to get it, because that would be proportional to the number of, if you took data and repeated it infinitely many times, that should be proportional to the number of times we get this, right? 1/6 times 1 plus 1/6 times 2 plus 1/6 times 3, you see a pattern evolving, plus 1/6 times 6 in this case. And formally, this is P of x times x over all x. So we sum over all possible outcomes and weight each outcome by the probability that it happens. Easy? In the formula for real data rather than a distribution, we had this factor 1 over n, which is the number of data points. Here you would replace it with a factor with 1 over the total number of weights, which would be 1 over 1/6 plus 1/6. 6 times 1/6 is of course 1. So, and that is because all probability distributions have to be normalized. The probability that something happens has to be 1. So we don't need to worry about this factor that you have in real data, because probability distributions are normalized. So let's calculate this. So in this case, this 1/6 factors out. So we have 1/6 times 1 plus 2 plus 3 plus 6. Well, let's write it all down, then it's easier to calculate. Plus 4 plus 5 plus 6. And that is 1 plus 2 plus 3 is 6, plus 4 is 10. That's 10. Plus this is 11, so this is altogether 21. So that's 21 divided by 6. Does that make sense? Is that correct? That is correct, I think, and that is 7 by 3, and that is, that can't be right. There's my mistake. 7 by 2, there's my mistake. So that's 3.1. Everybody happy? Also sort of makes sense. You have a flat distribution. The biggest number is 6, the smallest number is 1. Right in the middle is 3.5.
Talking about silicon detectors, and I to a certain extent assume that everybody of you know what a diode is. Nevertheless, I will explain the diode from scratch, because when we use a diode, we use it a bit differently, and for me, numbers matter. The next thing that I will try at a certain moment is to explain to you and show to you how a signal really forms. It's 2 slides. It doesn't do the topic real due diligence, because normally I need the full lecture just to explain that, but I think it's important. The other item is, whenever you see a silicon detector, you see any structure, the first thing you need to think about, doping concentration, effective doping concentration in silicon, and where you have higher N doping and higher P doping. I will explain all of that, but whenever you see a structure, that's what you should think. And before I really start, I invite every one of you, at any moment in time during the coffee break and dinner and lunch, come to me, talk to me. I'm happy to explain you in much further detail than what I can relay here. So let's say, why we're doing that? Why we're doing silicon detector? What is the historical aspect? They've been used since the 50s. They were there only for energy measurement. Today, we need them for fast and precise precision measurement. And the point is here, fast is in the order of 10 nanoseconds. Now, 10 nanoseconds, I would say, is the upper scale. It's more like 1 or 2 nanoseconds. And I will show you tomorrow that we can drive it down to 10 picoseconds of resolution. That precise, they're in the order of 5 micrometer. Now, 5 micrometers, the rule of thumb, is the easy value. We can go way below a micrometer of precision, and they're very good in energy measurement. They are in the order of an electron volt, while gaseous detector that were used here are normally in the order of 30 electron volts. So in the 80s, then they were used for charm quark tagging. I show a picture tomorrow. In the late 80s, then the lab experiments that they were used as a vertex tracker. And then during the 80s and in the 90s, they were then really used the first time at the Hadron machine at Fermilab. I show you a couple of pictures tomorrow, but I tell you, when these devices were deployed there, most of the people said, go home, don't do it, it will never work. Now we've proven that it works. So today it's literally all LHC experiment. It sits really at the heart and in large scale on all the future experiments. So they really give interesting beat tagging. We heard about beat tagging already before, and I will quote John Ellis, who is giving lectures in the next slide. They're incredibly good for the lifetimes and for the mixing of the background suppression. So before I go there, I just ask, why haven't they been used earlier? And that is, you need really microlithographic technology. which today is very easy. In the 80s and the 90s, that was almost not affordable. And then you needed also the readout electronics and the miniaturization. I also show a couple of pictures there. The miniaturization of the electronics was the key to be useful. So,
They say to run when it all goes dark, but I know where I'm gonna be. Next to the girl with a broken heart and a temper like the fallen leaves. I want to have you, I'm nothing without you. My music, it needs you, and I do. I breathe you. Tragic erases the look on their faces when they thought they'd break. We were ready for the earthquake.
So the depletion voltage at that moment goes, and this is also important, it goes squared. The depletion voltage you need goes squared with the thickness of the device. And that tells you, oh, but that's bad, because the thicker the device, even squared, the higher voltage I need. But then the thickness of the device at the same time gives you the amount of free charge carriers you have, because it's linearly proportional to the thickness. So you see, this already starts to be quite difficult because you need to have quite high voltage. Now you also see here, this is what I said before, the initial doping concentration, which is then the resistivity, gives another factor. And if you look now, the capacitance of these things is like a plate capacitor. So really basic plate capacitor, you basically start to have it here. It's a high voltage capacitance, then you draw outside the fields, you make the distance larger. That means the capacity, which then goes over this, goes smaller, because you increase the distance, you increase the field, and then of course done by the square. And if you have this as a capacitive measurement, then you see I increase the voltage, the capacitance lowers, and at a certain moment it doesn't change anymore. When does it stop changing? Anyone? When does it stop changing? When it depletes the detector fully, because then it just cannot draw the plate capacitor plates further up. And that is what you see here. Now you see from this to this distance here, this is the thicker detector. So this one is 500 micrometers, is 400 square meters, so I can drag out the plates even more, so the capacitance gets lower, but I also need a much higher depletion voltage because the thickness goes squared, 400 thickness to 500 goes much further. From here to here, this is a slightly different geometry. That is this A, this capacity point, and then the differences on the upper ones, the red and the green one, this is slightly different resistivity. So that's how we tune our detector. That's also in the silicon lab, how we measure the depletion voltage. And the depletion voltage at this moment, since all of this is clear, epsilon, ER, the mobility, and the size is clear, it measures directly the resistivity, thereby the doping concentration. Now a typical detector then with a PNN junction that we normally have is here, so it's not that we have a volume of same sizes, so normally what we do, we have 300 micrometer of so-called bulk material, which is slightly doped, like 10 to the 12, and then we have a strip or pixel, which is by 3 to 5 orders of magnitude higher dope. So you already can see this must have a much higher inreach because it is much more conductive. So without an external voltage, the depletion within this P region would only be 0.2 micrometer.
Next to the girl who can take my erases the look on their faces when they thought they'd break. We were ready for the earthquake. For the earthquake. They say to run when it all goes dark, but I know where I'm gonna be. Next to the girl with a broken heart and a temper like the fallen leaves. I want to have you, I'm nothing without you. My music, it needs you, and I do. I breathe you. Tragic erases the look on their faces when they thought they'd break. We were ready for the earthquake. For the earthquake.
For the high-lumen LHC. And the LHC detectors, in particular the tracker, is built of a scale to explore the range where the Higgs might have been and where we found it, and for the Higgs physics that we intend to do in phase 2. So that will continue to be the case going forward, and the tracker has really been integral to that effort. So I'm going to maybe try to lead in with the Higgs. First, just to point out where the tracker is, so this is kind of a cutaway of the CMS detector, so you'll see lots of different layers. The red that you mainly see are the muon detectors. If you go right into the very core of this, you'll see some blue here, which is the strip tracker, which I'll talk about, and you'll see this little greenish, yellowish thing in the middle, that's the pixel detector. The whole combination of those two things is the tracker. You may have seen this picture as well. This sort of yellow spot in the middle is indicating the centrality of the tracker within CMS. I should say that this photo is actually a montage. It's not a real picture. This part's a real picture, but this is a separate picture of the tracker that they've just kind of stuck into it. So whenever you look at this, you also see this at CERN. It's kind of fake. It's like photoshopped. So bear that in mind. If you take the cross-section, this is sort of looking along the beam pipe. If you look at this completely as a cross-section here, you'll see the layers of the tracker and the pixel detectors that I'll be talking about in this presentation. Okay, so we build trackers to do tracking. I should maybe first just define what tracking is, and a rough definition of this is just the reconstruction of the trajectory of charged particles using position-sensitive detectors. Now, as you know, there's a B field, magnetic field in CMS. We have a solenoid with an axial magnetic field, and that's what's providing a lot of the measurements that the tracker performs because it bends the trajectory of the charged particles. And from that, we are able to precisely determine a charged particle's charge, its transverse momentum, its initial trajectory, which is important when we're trying to do the reconstruction of the hard scatter physics that we care about, but also the propagation of that to things like the calorimeter and the muon detectors as well, so that we can do particle ID. And the impact parameters, which are basically distances away from the primary collision. Those are important for things like B tagging and tau tagging. So, and that's exactly what these things enable. So the extrapolation of the calorimeter to muon detectors, particle ID, and then also the overall energy flow algorithm that CMS uses to reconstruct the bands. And so what I want to point out is that with 4 leptons, the observation of the Higgs in this main channel, the 2 main channels were ZZ4L and diphoton. The observation of Higgs in this channel really would not have been possible without the tracker. There's no way to get those muons and electrons that I showed in the previous plot. Now, it's also the case that tracks, they are crucial, but they also feed into more physics objects that are also important for the experiment. So things like vertexing, defining the primary vertex, secondary vertices for things that have a lifetime, the reconstruction of jets, which is not just an energy blob, but there are tracks that are within this, Isolation algorithm, so sometimes you want to know if you have a photon, is it really a photon that's coming from some messy underlying event, or is it a clean Higgs thing, for instance? And then global event quantities like missing energy. And so what I would point out here is that normally you might think that the Higgs to diphoton analysis, they're photons, there are no tracks, they're not charged, right? So what's the connection to tracker? Basically all of these things, you still need a primary vertex, you need to isolate the photon. So even here, where you might think that the tracker is not playing the role, it's playing a very fundamental role, even if it's something like Higgs to photons. Okay, so in terms of the high luminosity LHC, so as you may have already heard from last week, I'm not sure, the LHC is being upgraded to provide a boost in instantaneous luminosity. That is going to give us data sets from high lumi LHC that are about 10 times the size of everything that we will have collected, so something in the range of 3 to 4 inverse Hadron. At that sort of scale, the high luminosity LHC is going to be a Higgs factory. It's not going to be just these little numbers and these plots that I'm showing, but we will have an overwhelming number of Higgs events to deal with. And that will allow us to measure couplings down to percent range precision, where they are now more around the 50% mark for some channels, for some couplings. Masses down to an MeV, rare decays that we don't have access to yet, and importantly, di-Higgs, which is something that we do not have enough luminosity to measure and to probe the self-coupling. So again, just as it was in the LHC, tracking is going to be central in the same way. Very large experimental costs. So to get those sort of luminosities, both the instantaneous and the integrated, we have to deal with a lot of pileup. And what pileup is a lot of these soft interactions that are overlaid on, if we're lucky, one very interesting Higgs event, for instance, or a dark matter event. And so that number is going to increase to of order 200 interactions per beam crossing. Right now in CMS, as of last week when we were running, we were averaging 64. And this was data taken from a high pileup run a few years ago that shows what 78 looks like. And so this is actual data from CMS showing the 78 different vertices, of which maybe one of those, where you have this red line, is the one that you're interested in. This is what it's going to look like for 140 pileup events in the high lumi LHC. You can imagine what it's going to look like with 200. And so you can see the density of tracks here is really going to make the job really challenging for the tracker and for tracking at the LHC. Okay, so that's kind of the introduction to the talk. What I'll do next is try to go through some general design considerations for trackers. So Ashfaq had asked me to talk about tracker performance. He didn't specify current tracker versus upgrade tracker, so I decided to do both, at least at a relatively high level. But to do that, first I thought to explain actually what our trackers are and why they look the way that they do. Okay, so in terms of design considerations, so I mentioned some of the things that we need to do: charge determination, momentum determination. The biggest one, or one of the biggest ones, is the determination of the transverse component of the particle's momentum. And the reason why the transverse component is important is because if there's any significant longitudinal is down the beam height, right? So anything that is really has a high or large longitudinal component, you're going to lose because you can't stick a detector directly in the beam height. Transverse components are also important because they're invariance with under boost with respect to the beam. So whenever we see a PT, if you move into the parton reference frame, it's the same PT because it's invariant. So that means that by measuring something in the lab, we have access to actually what's happening in the center of mass frame. Now, I mentioned CMS has an axial B field. As you know from the Lorentz force law, any charged particle that is moving in the B field will experience a bending force, or it's the Lorentz force. If you look at this in 3D, then you have helices. If your B field is axial, you'll have a circular motion around that B field. That's an overall movement in the longitudinal direction. And what we do is we try to determine the momentum, and this is just actually classical physics, but it applies just as well relativistically. So through these simple relationships, right, just the force law, we can relate that then to the transverse momentum of the particle. So what we need to do is basically figure out the radius of this thing. Now, what we want to do is to do this reconstruction for particles down to lowish PT. And basically, the limitation here is that we want to be able to reconstruct particles in jets to get a better momentum measurement, but we really don't care about the really soft stuff that's happening at all of those different pilot places. So to set the scale, we want something that is PT measurements down to about a GeV. And if you stick a GeV into this, you'll get a radius out of that that is about a meter. If you have a 4 Tesla field like CMS does. So what that is doing is already sort of setting the scale of your cylindrical tracker detector. It needs to be at least a meter if you want to be able to reconstruct particles down to 1 GeV. The specifications for the different parts of the tracker, so we have an outer barrel, we have an inner barrel, we've got end caps as well, inner discs, outer discs, which are the tach. And you'll see the pitches here where I list, well, first of all of the multiple layers, but you'll see the pitches for the different layers as well. And they are kind of what I said, they're around 100 microns for strips. The blue and red here, so the blue are something called stereo layers. This is where there's actually 2 sensors that are just tilted to actually give a coarse Z measurement as well. So it's not just R phi that we get, but we can get Z information. And if you trace a line, any one of these data lines, pseudo-rapidity lines through the detector, you'll find that basically we get 9 measurements for most of the detector. If you take these pitches with all of these number of modules, you end up with about something close to 10 million, it's actually closer to 9 million channels total for the strip detector. On the inside, we've got the pixel tracker, which is sitting just basically right on top of the beam pipe, so you can see the radii here are much smaller. This was upgraded, so from the original pixel, you can see here, they show the original, which is just 3 layers, and you can see what had happened for run 2, which is the phase 1 detector, which added a new layer, and essentially another end cap with some, or disk rather, with some geometry changes as well. And here again, the pixel size is kind of on order what I mentioned. I said 150 and 150, here it's 100 by 150. But you can see the channel counts versus strips is significantly larger, right? Because we've got a much more granular detector for pixels, which is helping us to measure the impact parameters.
Remind you, just put this to the side, I'm sorry, to remind you that one of the interesting aspects of single top physics is if you look at the ratio of the production channels, and that has to do between single top and single anti-top. The reason is purely you would naively expect it should be a factor 2, but this number ultimately will be too high energies goes asymptotically towards 1. And I challenge all of you in the audience to reflect why should it be 1 at very high energies, the ratio of single tops to single anti-tops. And there is a very fairly simple reason, but you should have understood that. So with that, then as another recap, we covered very briefly the chapter of searching for single top resonances. I hesitate to admit that there are other modes of checking single top physics, namely with single top in association with missing energy, and would be a channel for looking for instance, dark matter candidates. This is a big exotic subject which I have not covered in this lecture. I'm more or less concentrating on the top properties itself. Here you see once more as a reminder the mass limit of a regular single top production via an electroweak interaction with the so-called W prime. The W prime would come into existence as an additional weakly interacting boson, which, for instance, couples two left chiralities, and the fact that nature should, in the end, be symmetric, I mentioned before. But so far we have not found, and we can only give lower mass limits, and that you see here in those lines from CMS Atlas. Sometimes there are updates which I have not covered yet, but the physics itself is what counts, and had there been a deviation, we would have heard about it, of course, very intensively. So it's still the bottom line. You look for the upper limit of our data, as a function of a hypothetical mass limit of the W. So that's a cross-section for this production mechanism. That's cut around between 3 and 14 mass, which is a very, very large and disappointingly large number. Anyhow, this is when we look for exotic resonances, and so far we have not found deep deviations in the TB range, and that is what we have hoped originally for. So I come to a new chapter, that's decay physics. So far we have looked for the production of the single top quark, and with the hope of understanding QCD, pattern distribution functions, and so on, the whole production physics, but also the electroweak vector, and then finally the possible exotic additional channels to produce it. Now we look for the decay. And if you look, the top quark, of course, is a standard model particle. It decays weakly, only, as you know, I've shown you before. And you want to know it accurately. Here you find the evolution of the determination or of the estimate of the top quark mass with time. And I would guess that many of you were not even born when I started to do this mass determination, but now you are all here and listening carefully. We are not anymore there, but on this scale, which you see here, we are now here. That's where we are. And the mass has not changed ever since. The error has become a little bit smaller, that's all. This was the very first direct mass determination at the Tevatron by CDF. I'm proud that I've been part of this in those days, and it was just the pure evidence, not the direct discovery. This was made in 1994, just to see how many events we had. 1, 2, 3, 4, 5, 6, 7. 7 top candidates. And from this you could have already fitted the mass. And I'll show you in a minute how one does those things. And it was very close. And that came hand in hand, and you see at 93, there we are, with the indirect measurements given by lab data. And there are two reasons. One reason is with more data of the lab, you get more accurate standard model calculations and estimates of the mass. But also, I share, because this belongs all to our history, we had a very strong group in CDF that was a PISA group, and this group at home were also colleagues of the Atlas group in PISA, and of course they had copied together, and Atlas was the first to say, the top quark is massive, it's 170, something like that. And of course, no surprise. I mean, we just need this information, and so this is how it happens. So Aleph was not Atlas. Aleph, the lab experiment there, was the first to say the top quark is heavy, and that was just when we had this evidence, not yet published. Anyhow, that's the system. The this is the most important. Our detectors, when it comes to complex objects, they are not so accurate. You can measure very accurately the momentum of particles or the energy of electromagnetic particles like photons and electrons and positons. The charge momentum, you can determine very accurately the momentum of neurons. But the jet precision used to be around 100% of a square B. That means a 100 GeV jet would be known to about 10 GeV accuracy, much more. Now, CMS made use of this fantastic tracking detector, and it's a very, very accurate mental measurement through its high magnetic field to do something which was able to take all information into consideration and get a very, very more accurate measurement of the energy of the jet. Through particle flow method, we call that. So it was an interesting invention, and it has been used very much by the CMS to sort of supplement the calorimetry by itself. And the particle flow helps, but then you still also need the missing energy, and that comes from the overall energy sum in the calorimetry. So there are certain deficiencies in the accuracy of determining the energies. As I've told you, maybe the jet is now known to 3 GeV instead of 10 GeV, but still it is a fairly large number when you want to know what the top quark mass is in the 100 MeV area. So you have to calibrate your detector, and that has been done in a very, very good way, thanks to our high statistics. We have enormous statistics at the LHC. We have millions of events like W's. You can take top events and you look for the W which goes away from the on the other side, and you know it's the W. This is the entity which decays into two jets around 80 GeV center. And the center of mass system of this decaying object, that's a W, and you know the mass of the W is 80 point something GeV in very high accuracy. So you can constrain that. Those two jets must form an energy of 80 GeV in the center of mass. That is a way to calibrate in situ. We call it in situ calibration. Then, of course, the leptons you can calibrate, like the charged leptons, and the muons you can calibrate from epsilon events and psi events and Z events and so on. The calibration is the largest effort of doing a precision measurement. And that's why precision measurements take a long time. From last year, presented the COP 2023 conference, 172.52 GeV, plus or minus 140 in. But you have to take this into consideration, so you probably have an uncertainty of like 350 MeV as a total uncertainty, compared to 170 GeV, and that is the most accurately determined quark there is. All the other quarks and the masses are much more uncertainty in relation to the mass itself. So this is the most accurately measured quark there is. Anyhow, we don't need to go through all of this. I mentioned before, we have very many different analyses because we have different channels, and each of these analyses is an enormous amount of work and often results in a thesis per se. And then you say, is it worth it? I say, I encourage those who do this kind of work. Of course it's worth it, because of physics, which is behind the subject. So there's a different way to look for the top quark mass, and that is to look for the pole in the cross-section. Then I jump, and then I come back. Here you see, if you look for the invariant mass of a TT bar system, it would the cross section of this, if you vary, it would go through a maximum then when it becomes real. That is sort of a threshold effect which we hope to find in the LHC. But coming back to the pole, here it means that, to compare here. This is the top quark, the assumed top quark mass compared to the cross-section. And the cross-section, this is the cross-section versus the top quark mass. That is the theory. Why do we expect a pole? That's the propagator. So if you hit just the right mass, the cross-section becomes the maximum. And then for off-scale, for off-shell top quarks, this cross-section becomes smaller again. And this is an independent measurement of what we normally do when we reconstruct the decay products of the top quark, and where you mentioned already two lectures ago that of course we will have always the uncertainty given by the gluon field, the color charge. The color charge of course plays a role whenever you look at the decay products of the top quark. And here with the pole mass, the color charge doesn't play. That's the interesting aspect. But the accuracy is not so big because the cross-section measurement cannot be that accurate that you can have a 200 MeV accuracy in the mass of this. But you see here that is sort of the pole mass, it's 173 plus or minus 2 GeV, which is fine by itself. It's sort of, for me, a sanity check, but it's not something where you want to test electron physics with. So much for this. And here you see the essence of it. It's a G-Fitter program. It's not anymore being used very unfortunately. And if you click on it, you can get even the link to it. But otherwise, Google G-Fitter if you want to know more about G-Fitter. That has been very intelligent set of routines to determine some of the parameters. And this one is, for me, the most interesting in this context.